on absolute value functions. So we're going to start by looking at kind of what it is, and hopefully at this point in your mathematics career, you understand that even though most students will tell me that, oh, it just makes everything positive, that is true, but hopefully you understand the reason behind that is that the absolute value function measures the distance of your input from zero. And because distance is neither positive or negative, then it's always going to be positive. So I always give the example of if I were to drive from here to Austin, all right, and then drive from Austin back to here, ultimately I'm driving the same distance even though I'm going different directions. So directions can be positive or negative, but distance is going to be always positive. So the absolute value function is commonly thought of as providing the distance the number is from zero. Okay? And I don't think you've probably ever seen this as a piecewise function, but here it is in terms of broken down into what it would look like for a piecewise function. If you plug in a negative number, you end up doing the opposite of that negative to make it a positive. All right, but again, most students will see this and think, okay, I know that function. It's from my toolkit. Now let's look at a quick example. It says, students who score within 20 points of 80 will pass a test. Write this as a distance from 80 using absolute value notation. So when I'm thinking about this, right, I know I have to do absolute value, all right, and it says a distance from 80, so I'm going to use subtraction, all right, and again, I'm looking at this compared to being 20 points within 80. So if I got 100, then I'm 20 points from 80, obviously I pass. If I got a 60, that's 20 points from 80, so I pass. But there are some other scores in there that would also work, like 70, 90, 75, 85. And if you were to take one of those numbers and subtract 80 and then take the absolute value, you would always be less than or equal to 20. So the symbol here that's going to make the most sense is going to be less than or equal to, because you have so many different options. All right, graphs of absolute value functions. We actually did a little bit with absolute value. One of our examples in the transformation section did use the basic toolkit absolute value function, which is in blue right here. All right, so this is our absolute value of x. And the key thing that I want you to take away from that is when you graph this v, when it's the basic one, your slope of your lines are going to be positive 1, and the other one's going to be negative 1, right? So if I looked at the slope here, that's up 1, right 1, and then up 1, left 1. So those are slopes of 1 or negative 1. So when you move it to the right 3, all right, moving it 3 units to the right, you'll notice that's inside the absolute value thinking opposite. That's the one in orange here. Looks exactly the same, but we just moved it 3 units to the right. The next one is going to be this vertical stretch. So that number 2 out in front, that takes that slope, which I said was 1 or negative 1, and becomes 2 and negative 2. So up 2, right 1, and up 2, left 1. So you'll just notice that the V is just a little steeper. And then finally, moving that one that's been moved to the right and vertically stretched, moving it now up 4, we're taking that turquoise one, and now we're moving it 4 units up. So the red one should look exactly like the turquoise one, just 4 units up. All right, so again, all those discussions we had about moving things horizontally, vertically, stretching, compressing, reflecting, all that still is here, even if we're just talking about absolute value functions. So let's try to write an equation for this one. So when I look at this one, I always, and this is just habit, I always plot the parent function, right, from my toolkit. So I'm going to plot at 0, 0 for my vertex, and then I'm going to plot my slope of my lines at positive 1 and negative 1. So again, as I said, that's something that you should have committed to memory at this point. Now, when I go from my one that I drew in black to one that's in blue, if I were to count how far I'm moving, so I'm going to move 1, 2, 3 to the right. So that's 3 units to the right, or 3R. And then I'm moving 1, 2 units down. So that's my horizontal and vertical shift. So I'm going to go ahead and write that. So that's going to be f of x equals, all right, remember thinking opposite here, x minus 3 inside the absolute value, and down 2. And you might be thinking, oh, I'm done. But if you notice that the v that's in blue looks like it is steeper. And I'll show you a quick way to do this. But the way to do it algebraically to make sure you got the right answer is to insert a letter A standing for the constant that we've talked about in the past for the vertical stretch or compression, and choose a point that's on this function that we can plug in to solve for A. So you can choose any point here. I'm just going to choose this point, which is 4, 0. So my y value, which is the same as f of x, is 0. I'm going to leave that A, plug in that 4 for x, and I'm going to solve for A. So that's 0 equals A times the absolute value of 1. Right? The absolute value of 1 is going to be just 1. So if I move that minus 2 over, I get A equals 2. Now, some of you out there are probably shouting, saying, yeah, I already knew that. Totally fine. And if you look here, you should be able to see that if you start at this new origin, and if you move to find the next point, that 4, 0, you're going up to right 1. So that just confirms that A should be 2. Don't forget, as I mentioned with my other classes, and I'm sure your teachers in previous classes have said, once you find all this, please write the answer, right? Because technically you have it, it's just in pieces. So our function is 2, that's that vertical stretch, times x minus 3, that's that horizontal shift 3 to the right, and then minus 2 is that 2 units down, vertical shift. All right, so that's it. That is our function that shows this graph that's in navy. Okay, let's do the same thing, but without giving a graph. It's just telling us verbally what's been going on here. So we have our function. It's telling us it's shifted left 2 units. So I'm going to think opposite inside the absolute value, so x plus 2. Then it's vertically flipped. This can be confusing. Vertically flipped means across the x-axis, so your y values are changing. So that means that the negative sign for the reflection has to go outside of your absolute value. If this had said horizontally flipped, instead of vertically flipped, if it had said horizontally flipped, then the x that's inside the absolute value would have to have the negative. So the negative would go right inside next to the x. But it doesn't. It says vertically flipped. So we're going to put the x out, or the negative outside. And then 3 units up will be that plus 3. So this is the answer. All right, now the last kind of part here is thinking about how to solve absolute value equations. And you guys have done this since your days in Algebra 1 and Algebra 2. And the key thing here is because you have, when you're able to plug in a negative and take the absolute value, it turns into a positive, and obviously plug in a positive, take the absolute value and turn it into a positive, you actually have the potential, like I say always, the potential for 2 answers or 2 solutions that would make your equation true. So you'll notice that the key steps here are to isolate the absolute value. And once you do that, you're going to set your value, or I should say your expression that's inside the absolute value, equal to the positive number that's outside and equal to the negative number that's outside. So you got 2 options potentially that are going to make that true. All right, so I'll show you how to do this, and then we'll talk a little bit about kind of something that could happen that should be kind of like alarm bells for you, okay? All right, so this function says the absolute value of 4x plus 1 minus 7, and I'm going to solve for the values for x that are going to make this equal to 0. So essentially, my x-intercepts or solutions. So when I do this, the absolute value is not isolated. I notice that minus 7 right here is not inside the absolute value, and it needs to move to the other side. So I have the absolute value of 4x plus 1 equals positive 7. So what I always tell students here is take a moment, and once you've isolated it, right, this checkpoint, just analyze what you've written. I see no issues here, but in the past, I'll have students that are really solid with the steps that I'm going to show you how to do, but they won't take a moment, just 10 seconds, to think about what it's saying. So like, for example, if I made this 7 a negative, you could immediately write that there are no solutions because there's no values that when I plug into my expression, multiply it by 4, add 1, then take the absolute value of it, will ever give me a negative, right? That absolute value step at the very end means that it's always going to be positive. So if you notice that your absolute value is isolated and set equal to a negative constant, that's a huge red flag, and you can immediately say that there are no values that would work. So I'm going to go ahead and take that away, but ultimately, you want to be on the lookout for that. So now I'm going to write 4x plus 1 is equal to negative 7, right? Because if that's true, I will get a solution. Or 4x plus 1 equals positive 7. So either one of those will work because when I take the absolute value of negative 7, I get 7. And when I take the absolute value of 7, I also get 7. So both would work. I'm going to move that 1 over and get negative 8. So x equals negative 2. Same thing over, move over the 1. It's going to be different answers, but the work is going to be exactly the same. So that's 6. 6 fourths reduces to 3 halves. So these are my two solutions that would make this absolute value function become 0. Let's try another one. So let's set this equal to 0. 2x minus 1, that's the absolute value of that, minus 3 equals 0. Again, it's not isolated, so let's move that minus 3 to the other side to make it a positive 3. Do that 10-second check. Is your absolute value equal to a negative? No, so you're okay to continue. So we set 2x minus 1 equal to negative 3, or 2x minus 1 is equal to positive 3. And I want to caution you guys, when you get to this step, when you're writing this statement that includes the word or, I should not see any more absolute value symbols, right? So if you look up here with our work, when we wrote this step and set these two equal to a positive 7 and negative 7, make sure I should not see any more absolute value symbols. All right, so I'm going to add that 1. Negative 3 plus 1 is negative 2. And then on this one, I'm going to add that 1 and get 4. So I get x equals negative 1 and x equals 2. So that's kind of the process for how you want to solve these absolute value equations. Now, the last thing, just to take a moment, is should we always expect two answers when solving these? And I kind of already alluded to this earlier, that you have the potential for two answers. So for example, like I said earlier, if your absolute value is isolated and equal to a negative, you're not going to have any x-intercepts. So this right here, this example A, and it is an example where when you isolate the absolute value, it would be equal to a negative. So in this case, we have actually 0 solutions. And in letter B, this would be when your absolute value is isolated and set equal to 0. So you actually only have one solution, right? This 2, 0 is your one solution. So you can't set something equal to 0 or negative 0, right? 0 is neutral. So in this case, your absolute value would be equal to 0 when you solve. And then letter C, this is one that we just, not that we just did, but this would be similar to what we just did, where you have two solutions where your absolute value is equal to a positive. All right, so that's it for absolute value. Don't forget to do the practice problems.